Welcome to iTTV for Form 4 Chemistry. Today's lesson, diffusion. If we recall back once again to our lower secondary, we learned about diffusion. We learned about diffusion as particles spreading out, or particles moving from an area of high concentration to an area of low concentration. We used the idea of diffusion when we talked about how gas in the alveolus moves into the bloodstream, or how digested food moves from the small intestines through the villus into the bloodstream. Diffusion is very important to us, mostly because it helps us prove one of the statements of kinetic theory. So let's get into diffusion and then answer these questions on kinetic theory. Diffusion can also be defined as when particles move at random from an area with high concentration to a less concentrated area. The key statement here is move. If we remember back to our kinetic theory, we have two statements. The first statement in kinetic theory is that all matter is made up of tiny discrete particles. In the last lesson, we looked at these particles, atoms, molecules, and ions. Now we want to look at the second statement. The second statement says this: all particles are in constant, and this is the key word here, motion. All particles are in constant motion. Now, if we can understand that all these particles are in constant motion, we can understand how things start to move or how things behave. But what we've got to prove is that all particles are in constant motion. As with all things in science, we must be able to prove the statement that we are making. Diffusion. Particles in matter are in motion. How do we prove this statement? Well, in order to prove something, we need to do an experiment. And since the time of Galileo, who changed our way of thinking about science from a theoretical to an experimental science, the only way to prove something is by an experiment. Diffusion occurs fastest in gas, slower in liquids, and slowest in solids. Now, if you imagine all of these three things, you can easily understand, and we've also talked about this in our lower secondary. Solids, the particles are vibrating, they can't really move. In liquids, the particles move slowly. And in gases, the particles move very fast at high velocity. And this basically relates back to what we've just said, that diffusion is fastest in the gas and slowest in a solid. Diffusion experiments. Potassium permanganate in water. So what we're going to do in this experiment is quite simple. Here we have two beakers of water with roughly an equal amount of water. What we want to do is investigate two things. One is that statement that we have up there. All particles are in constant motion. Very essential. We need to prove this. We can't just say kinetic theory says that. We need to prove that kinetic theory is correct when it says that particles are in constant motion. So over here, I have a bit of liquid potassium permanganate, which has got this wonderful purple color, so we'll clearly be able to see when particles are moving. And over here, I have some solid potassium permanganate. So this is the same material, but I haven't dissolved it in the water yet. So what we're going to do is we're just going to put a bit of both of these into the water and then figure out and analyze what we've got and sort of like make a conclusion. We'll start with the first one. So I'm just going to take a bit of potassium permanganate and then I'm going to just drop 1 or 2 drops into here. Okay, and you can clearly see what's happening is that the purple color is spreading out slowly. Okay, the purple color is spreading out, and as this purple color spreads out, it must mean that the particles are moving. Going back to the statement we've made, particles are in constant motion. So what this experiment is proving to us is that particles can move. I'll just put a little bit more inside here because it looks ever so nice. Science is fun, isn't it? When you do things like this. And you can see that almost the entire water now is turning into this purple color. Science is truly fun. Okay? Because the particles are moving around. Now we'll do the same thing but with the solid. Here what I want you to try and notice is that it spreads out just a little bit slower. Particles move faster in liquid and slower in solid. So we'll just take a bit of this, okay, and then just drop it in here, like that, and wonderful, isn't it? You can look at that purple color. Firstly, you'll notice that the purple color has dropped to the bottom. That's because solid is slightly denser than liquid, so it's dropped to the bottom, and then slowly it is spreading out through the bottom. Okay, and it'll take much longer for the water inside here to turn purple. You can see that we've got 2 layers. The lower area here is quite purple already, but the upper part of the water is still quite clear. Now, the upper part is clear because it takes longer for the potassium permanganate to spread out. Why? It's in solid form. So what do we understand from this experiment? 2 things. 1, particles are in motion. 2, the particles in solids move slowly, particles in liquids are faster, and obviously particles in gas are the fastest. Diffusion. Conclusion. Proves particles in matter move. So here we have basically 2 of kinetic theories being proven. We've already done matter is made of tiny discrete particles, atoms, molecules, ions. The second statement, particles are in constant motion, we've proved today. In both of the experiments that we did, the color of potassium permanganate spread out, and when the color spread out, it proved to us that the particles are moving. The third statement of kinetic theory is if the temperature increases, the kinetic energy of the particles increases, which means they move faster. If I was to put this beaker underneath a Bunsen burner, what would happen is as the Bunsen burner heated up the water, the particles would start to move faster. And this would prove also for us the last statement of kinetic theory. Please, kinetic theory is very, very important. You need to understand it because it is the fundamental stuff that we need when we are thinking or answering or creating chemistry. Because particles are the things that we play with in chemistry. Now that we've done this, let's try a few questions on what we've done so far. Number 1, what is diffusion? So try and recall what we've done in this experiment. Diffusion is what? Let's have a look at the answer. The particles move from a highly concentrated region to a less concentrated region. Let's move on to the next question. Diffusion is fastest in what state? Remember, we have 3 states, solid, liquid and gas. In which state do you think the particles are moving the fastest? Let's have a look at the answer. Gas. Let's try one more question. What do diffusion experiments help us prove? Now we've done the two experiments here, putting the potassium permanganate inside water and putting the potassium permanganate crystals, solid potassium permanganate, inside water. What did both these experiments prove to us? The answer is particles are in constant motion. So remember, this is the key and fundamental thing that diffusion experiments help us understand. Particles are in constant motion. Now, what's also important to remember is that these particles move at different speeds. Remember, we've said gases are the fastest, solids are the slowest. But within each of these groups also, we have differences. A heavy gas will move slower, a lighter gas will move faster. The three states of matter. The three states of matter are solids, liquids, and gases. Solids. Key points. Closely packed, orderly arrangement. So now we want to have a look at our solids. The idea of solids is you need to be able to draw how a solid structure is and know the key points or the key characteristics of solids. Once again, we did do this in our lower secondary. This is just a recap with a bit more detail. So let's go to the board and start with our solids. So we begin with solid. The particles in a solid are drawn in a particular way. Like we've said, they are closely packed so that they are quite close to each other. Secondly, we said they have an orderly arrangement, which means that, as you can see here, we have one layer neatly placed upon another layer. So the first two key points were, number one, they are closely packed. Number two, they have an orderly arrangement. So this is our solids. The particles are very closely packed to each other. The particles, one layer sits neatly on top of another layer. We have what is called an orderly arrangement. Now it gets a bit tricky when you have so many words to try and think of. So here's a hint. Use what we call mnemonics. A mnemonic is where we try and make statements or sentences or rhymes or silly words that will help us remember. In the case of closely packed orderly arrangement, we can try and take the first letters. Let's take these, clo, okay, and take P-A and K. So we get a word like this. Clo, pack. Clo pack, and it sounds also quite right. Clo pack, closely packed. And then we need orderly arrangement. A bit difficult with orderly arrangement. Well, we take the O, R, or, and then take ainge with the E here, which gives us the word orange. So if you can remember this mnemonic, clo pack orange, clo pack closely packed, orange orderly arrangement. So the two key things of solids can be remembered by just a single mnemonic silly word like clo pack orange, closely packed arrangement, okay, orderly arrangement. Let's move on to other key things that we need to know about solids. Solids, key points, strong forces of attraction. Now in a solid, you will notice the particles are very close to each other, which means that the forces of attraction must be quite strong between them, must be holding these particles close together. So please, you need to remember they have strong forces of attraction. Solids, key points. Particles vibrate in a fixed position, fixed volume and shape, cannot be compressed. All of these are the things that you need to remember for your solids. Closely packed, orderly arrangement, Clopac orange. Strong forces of attraction. Also a bit of a mouthful. Try and make a mnemonic out of it. Strong, maybe you take the first letters, straw, force, attraction, AT, strove for at. So if you create a word like strove for at, you'll remember strong forces of attraction. But the last part, there's a lot of information. Vibrate in a fixed position, fixed volume and shape, cannot be compressed. Now these are key facts that you need to know about a solid, and if you can come up with a mnemonic for them, very good. If not, you need to remember these because these are essential things and you'll always be tested on these points. Let's move on to liquids. Key points: closely packed, not arranged in order. So if we move to our liquids, let's do our liquid over here. What we have with our liquid is that the particles are closely packed, but they are not in an orderly arrangement. We tend to draw them in groups of 2 or 1. So you draw like 2 of them here, 1 separate, maybe another 2 here, 1 here like this. They are still close to each other, but there is no real orderly arrangement to them. So you may be able to take the word Clopac orange and change it to Clopac, closely packed. Not orderly arrangement. Okay, sorry about the R here. Okay, so Clopac, orange. Clopac, closely packed, orange, not orderly arrangement. And by using this mnemonic, 2 words, very easy for you to understand the basic idea of solid and liquid structure. Let's move on to the other key points of liquids. Key points: strong forces of attraction, but weaker than solids. So here the forces of attraction are still strong, but because the particles are slightly further apart, here they're slightly further apart, over here in the solid they are much closer together. So the forces of attraction must be slightly weaker than in solid state. Key points: particles can move slowly, no fixed shape, takes shape of container, fixed volume, cannot compress. So these are the other key points of a liquid that you need to know. Now, because they can move, what we can do to help us understand this movement is, when you draw a liquid, put a small arrow on it. If you put a small arrow on it, this indicates that these particles are able to move around like so. Notice the difference? These particles have got arrows so that they can move around. These only vibrate in a fixed position. Illustrate to yourself these things. It vibrates in a fixed position. How do I show that? Well, in your diagram, just put 1 or 2 little marks at the side here, and these will help you understand when you look at your own notes. Oh, they got little marks at the side. These vibrate. These have got arrows. They must be able to move slowly. If you do all of these things, the diagrams and the notes that you create will help you understand your chemistry much better. So, liquids. Just a quick recap. Clopac orange. closely packed, not orderly arrangement. What are the other key things? Particles can move slowly. No fixed shape. Takes the shape of the container. But they're still close together, cannot be compressed. Now let's move on to the last of our states, which is gas. Gases. Key points. Particles far apart with random motion. So how is it that we draw a gas? Let's move over here and get the final one up here. This is our gas. And when we draw gases, we tend to draw maybe 2 or 3 atoms or molecules, and that's it. So you draw one over here, put a longer arrow on it. Longer arrow means it's moving much, much faster. Random motion, so the arrows can be in any direction that you like. And that's more than enough when you draw a gas. Try to keep it simple, okay? Clear to the point and simple. So, particles far apart, random motion. Key points, weak forces of attraction. A bit like, if you imagine that it's the Sun and the planet Pluto, because these particles are so far apart, just like Pluto is so far from the Sun, the gravity between the Sun and Pluto must be weaker compared to Mercury or any other planets that are closer to the Sun. Well, similarly here, because these particles are very, very far apart from each other, the attraction between them must be quite weak. So the force of attraction in the gas is said to be weak. Solids, strong. Liquids, strong, but weaker than solids. Here, when we get to gases, there is no strong anymore. It's straight to the word, weak forces of attraction. Key points. No fixed shape or volume. Takes shape and volume of container. So as you know, a gas, the particles are so far apart, the volume of a gas is the volume of the container it is in. The shape of a gas is basically the shape of the container that it is in as well. And because the particles are so far apart, it is very easy for me to push them closer together. Okay? I can easily push it closer together, which means gases can be compressed. Again, most of this material you learned in your lower secondary. Now, it's not a question of, oh, I learned it in my lower secondary. Now it's a question of, I must know this. Because this is the last part of kinetic theory. Kinetic theory starts with, number 1, everything is made out of tiny particles. Number 2, the particles are in constant motion. Number 3, if the temperature increases, the kinetic energy increases. Finally, we get to solid, liquid and gas. And when we are in solid, liquid and gas, we use kinetic theory to explain solid, liquid and gas. If you don't know your kinetic theory, you're not going to be able to explain these 3 states. The motion in the states, the arrangement in the states, the forces of attraction in the shape, in the states, their shapes, their volumes, whether you can compress them or not. All of this is explained using kinetic theory. You must know your kinetic theory like the back of your hand. Changes of states is caused by heating or cooling. Now, we also did this in our lower secondary, and a change of state is where solid changes into liquid, liquid changes into gas. Now, think about it. This is really, really quite weird. This solid, where all the particles are close together, suddenly spreads out and becomes this, a liquid. And if you keep heating this liquid up, it spreads out and becomes this gas. I mean, if you just think about it, there must be some weird forces or some weird interaction occurring here that allows one state of matter to just change into another state of matter. Remember what we've done today? We've proven that all particles are in constant motion. We've looked at solids, liquids and gases. We've understood the characteristics of each. I've showed you how to use these little mnemonics, Clopac orange, Norange, okay? How you can use those to help you reduce the number of words you have to remember. We've now finally talked about solids changing to liquids, liquids changing to gas. But we're going to do that in the next lesson because we don't have enough time today. So thank you for watching iTTV, and I'll see you in the next lesson. Bye.